we have to move forward. And our next speaker is Evgeny Kozhevnikov, and Evgeny will talk about the dispersion properties of a heteromodular medium on example of sandstone. Evgeny, it's all yours.
Good afternoon, and I want to present you a report, Dispersion Properties of a Heteromodular Medium. The short agenda on the slide. The first is introduction, research methodology, discussion of research results, and conclusion. First of all, I want to say about that during the production of oil or gas, there are several factors that can result the wave pressures in the wave of pressure in the formation. There are dynamic loads that can lead to changes in mechanical and filtration capacitive properties. Also drilling, during drilling, the initial opening of the productive formation and the vibration of the porous rock that created by the bit contribute to a deeper penetration of the mud filtrate into the porous media. So it's also necessary to know that the change in mechanical properties during drilling under the influence of dynamic loads from the bit. So also during field development, shutdown of production or injection wells contributes to the occurrence of waves pressure in the reservoir. So there are also well-known methods of enhanced oil recovery based on the wave action on the well bore. So I want to say that knowledge of the elastic properties of behavior of elastic properties of rocks, it's quite important question. First of all, I want to tell you about research methodology. So existing devices for laboratory studies of the influence of dynamic loads on elastic properties are machines for uniaxial or triaxial compression. For research, cylindrical rock samples are made up to 250 millimeters of length and 76 millimeters in diameter. Samples are prepared, glued to the plates of the machines, to the apparatus, and during loading onto a rock sample, dynamic vibrations are created with a frequency up to 2 kilohertz. Sorry. So also I want to say that existing machinery can create the small amount of loading, only up to 0.5 MPa. So this is the main disadvantage of existing machines for dynamic loading of rock samples. On the basis of the University of Aberdeen, we have assembled an apparatus for studying the dynamic effect on rock samples. The apparatus consists of an oscillation actuator that connected to oscillation generator, and also this machine have load sensor, axial displacement sensor, and here we can see rock sample that is already installed on the installation. This installation has the following characteristics. So we can study uniaxial dynamic loading. The size of samples up to 24 millimeters. Maximum dynamic load is 1 kilonewton, 1.1 kilonewton, and frequency we can use from 20 to 100 hertz. So the research program included the attachment of the sample, creation of a preliminary statistic load on it. We create preliminary loading 500, 700, 900 Newton on sample. And then acceleration generator is launched. And by changing the frequency and voltage of current, we can create some vibrations. Also, we record all data that we got from sensors, and by specially written program in LabVIEW, and after that we got results and process them in MATLAB. So main recorded parameters is the force, axial displacement, and lateral displacement. Also, there are some another parameters that we also have in addition. This is a method of data processing. First of all, we take time, which we have some frequency, that we have some force amplitude, and after that we got this short period of time in 2 seconds. And in these 2 seconds, we got average delta F, change of force from minimum to maximum, peak to peak. Also, we have axial displacement, also delta L, from minimum to maximum, peak to peak. Also, lateral displacement and another properties. By knowing these properties, we can calculate Young modulus, dynamic Young modulus. Also, we can calculate dynamic Poisson ratio, and so on. So another issue that needed to be resolved is the selection of the size of sample. For example, if we use standard size of sample of 50 millimeters in diameter, the load that we can create it's about 50 kilonewton to be in elastic zone. By halving the diameter of the sample, the required load can be reduced. Yes, here we can see results of static loading of rock sample with diameter 24.7 millimeter. Also, we can see that our apparatus cannot operate in elastic zone that we need. That's why we decided to reduce the size of sample in diameter 7.62 millimeter. And here we can see that we can operate by our installation in elastic zone. So we can create dynamic loading, and this dynamic loading will be only in immediately in only elastic zone. So the results that we got after dynamic loading of sandstone samples, and here you can see the dispersion of Young modulus. This graph shows you dependence of Young modulus from frequency and loading. So not loading, it's stress. Stress is generated in rock sample. We can see that stress that is generated in the sample affect the Young modulus is much more higher than frequency that we use while testing of rock samples. So there are similar results of similar dependencies were obtained in the works of other researchers. So we can see also that other researchers got the same graphs that shown us that dispersion of Young modulus during dynamic loading. Also, we can see that saturated samples are more affected by dynamic loading than dry samples. In our case, we used dry samples, and you can see that our samples are more affected by these results. This is because we used much more higher amplitude of stress. That's why our samples, our dependencies are more our dependencies have this character. So there are several reasons of this phenomenon. The first is rock compaction, underloading. This phenomenon, I mean dispersion of Young modulus while dynamic loading. First is rock compaction underloading. According to the well-known fact, an increase in the Young modulus occur while compaction of rock respectively with large loads more the Young modulus. So when we apply the force, micro cracks, pores closing in the rocks, and rock is compacting, and Young modulus is increasing. This is the first reason, and also we can see that for rocks that have more elastic properties, for example, shales, they have such kind of dispersion. So the second reason for dispersion is the phase shift of energy and energy dissipation. In some works, it was shown that when the natural frequency response of the sample and the transmitted load to the match, a phase shift can occur between the applied load and the resulting deformation from this load. As a result, the total deformation decreases and energy dissipation occurs. And these graphs, you can see the phase shift that occurred while sample loading. For example, in frequency 30 Hz and frequency 40 Hz, we can see that the phase shift occurs in both cases. So by this phase shifting, energy is dissipating, and we see this picture about Young modulus dispersion. Sorry. So also we can compare two different cases. For example, frequency is the same, 40 Hz, and they're different force peak to peak, 50 Newton and 125 Newton. So we also can see the same picture, that there are phase shifting and energy dissipation also. So this is all what I want to say. I think that my topic is not relevant to this mini symposium, to the theme of this mini symposium, but I think it was interesting for you to hear about something of rock properties, how they change under dynamic loading. So thank you. I would like to ask you a question.
Thank you, Evgeny.
Answer your question. Sorry.
Actually, I'm pretty sure that your topic is relevant, and tons of interesting information I extracted for myself. So we have 5 minutes for questions and answers. Somebody wants to ask something? Nikolai, please go ahead.
Okay. Thank you, Dmitry. Just my question was about the experimental facilities, because you said that in the University of Aberdeen you created just the better facilities for this experiment and compared it to the existing machine for just loading and but I could not feel the comparison because for that machine you provided just the pressure, so force per cross section, and
yes.
for your machine you provided force loading, and it's impossible to compare force and just pressure. So can you provide the comparison of the existing machine and your facility, which is better in some comparable units, for example, in force or in just tension?
In force, okay.
In force.
Can I ask you? Yes.
Because there it was 0.5 megapascal, but just can you convert it in force?
So it depends on the size of the sample.
Definitely depends. That's why.
Yes.
That is the reason for my question.
The limit that we have in our installation is a force about 1 kilonewton, 1.1 kilonewton of dynamic force. Is a limit of actuator that we used for this installation, magnetostrictive actuator. That's why we decided to reduce the size of the sample. To compare these machines,
the size on that machine as well, because if I reduce the size on that machine, I could have just obtained maybe some better result or not. What is the?
If we reduce the size of machine?
No, the size of sample.
If we reduce the size of sample, of course, we got some not incorrect, but some results that are under question, because we use the sample that have little size. Also, the size of grains also affect on the properties of these samples. Also, when manufacturing, we can create cracks of samples. It was a quite challenging question to create samples, a number of samples for this research. Samples of this size.
Okay, thank you.
Thank you. More questions? We have a time for one question. Let me ask you something. It's not like a research question, it's more like about the organizational question. Do you know the research team of Professor Stanchits at Skolkovo Institute of Science and Technology?
No, I don't know.
Maybe it would be interesting for you to connect to Professor Stanchits, because his studying similar things, mainly for geomechanical and fracturing, cracking, but the setups, the experimental setups you've described are kind of similar to what he has here in Skolkovo, and probably you will find some mutual ground to discuss and to develop some research ideas together.
Okay, thank you.
Okay.
Good afternoon. I am one of the co-author of the paper, Marian Wiercigroch from Aberdeen.
Hello, Marian.
Hello, how are you? If I could explain Nikolai. So Nikolai is absolutely correct. The results are not 100% comparable. We try to be as close as we can. The main kind of learning from it is the trend of the results, not the results in absolute, because I don't think so we are able to go to the same I would say level of stresses as Zhenya was basically citing from the literature, but the trend of the result is also basically is correct. With regards to the challenges which we had, we had a transducer which didn't have enough basically power. So the Zhenya, this Zhenya and the other one from Perm, they try to cut the samples which are extremely small. That brings the danger because we absolutely had no control on the fracture process within the sample. So that has to be taken with a pinch of salt. I think the indication from the results point in the right direction, but I wouldn't take them. I wouldn't put my mortgage on it. I would say that way.
But of course, it could be more reliable to have just the compression from all sides.
Yes, yeah, I cannot agree more. Yeah.
Yeah, but nevertheless, well, the results are very interesting. Very interesting. I was impressed, really.
Thank you. Yeah. Okay, just a small, basically, additions to Zhenya presentation. Okay, so I'm done. Yeah, thank you.
Yeah. Thank you, Marian. Thank you, Nikolai. And of course,
not at all. Thank you.
Thanks to Evgeny. So we have a good discussion